I'm going to introduce Markus Stöckli, Senior Principal Scientist at Novartis Institute for BioMedical Research. So Markus is going to talk to us about combining the Echo MS Plus with the 7600 ZenoTOF instrument, which makes it an ideal system for covalent binding screens. So we're going to cover speed, so measurements from a full 384 well plate in less than 15 minutes, or from a 1536 well plate in less than 1 hour. Talk a little bit about precision and the low injection volume that supports repetitive measurements, and high data quality that allows for full automated processing, delivering immediate hit list output. Welcome, Markus. Over to you.
Hello, everybody, and thanks for listening into this. This presentation is actually broadcasted from Basel in Switzerland, where we have a part of the research organization of Novartis. So in my role as a scientist at Novartis, I'm kind of in technologies and try to support our colleagues in drug discovery with new technologies. And obviously, when somebody comes up with something new, we are interested into it. We want to see how we can apply it, and most importantly, how it can do better in drug discovery. And I think with this technology which we have here, there is really a step up, which allows us to do some things better and faster. But before we go into it, I want to thank the people involved in that. We had the chance to evaluate this system as part of a customer evaluation program. This was made possible by SciEx, the people at SciEx, in particular Parik and Han, for their support. Then in this process of evaluating this technology, we had many teams looking into these systems from early drug discovery into late stages. And so that's why the list of people I like to thank is quite extensive here. So you saw the video before, and let's get some technical aspects into it before we go to the application. So in our field of LC-MS, we typically use needles to sample into particular wells for samples, right? So if we receive a sample, we clean it up, and then we fill it into a plate or fill it into flasks, and then we put it in the autosampler. Then the autosampler takes a while and then puts a needle into it, injects it in the mass spec. This process alone takes some time. And so the idea here is very simple. How could we overcome this step and just directly from the liquid go into the mass spec? Now, parts of it is not novel. For those of you who have worked in the high throughput field, then you know these ecosystems. Basically, it's an acoustic dispenser which takes an acoustic wave to detach droplets from a surface of a liquid. And so these droplets you fire up typically in a daughter plate. So basically, this is being used for plate replication, for cherry picking, for every application where we need small volumes. Now, the idea of SciEx was very simple. How about we remove the daughter plate and just put a mass spec on top, right? And so then we directly shoot these drops into a mass spec. Obviously, it wasn't that simple, right? Because you cannot just flip a mass spec and put it on top of the ecosystem. So the system which they applied is basically they have a tube connecting from the echo sampling system into the MS. And this tube needs to be fed constantly with liquid. This is being done with a solvent, which you bring into here. And this is kind of a coaxial setup. Basically, you feed in solvent, which is being sucked into the MS. And on this side, we have the regular electrospray, as you have in every single electrospray system. Then this part here is open. So basically, one shoots directly drops into this vortex, and this drop is then being transported into the mass spec. Now, I already hear you talking, well, if you shoot into this liquid, then you have a huge dilution going on. And then this dilution will lead to less sensitivity. I think there is a dilution, and this dilution is significant. It's a factor of 5,000. But I think this dilution, which can be seen negatively, is actually very positive because it allows it also to go into this buffer with very high concentrations of salt because we have this dilution. Let's say we have 100 millimolar salt concentrations. By the time the sample reaches the other side of the capillary, it's way below millimolar, and it's compatible with mass spectrometry. So basically, we have achieved something which is perfect. We can directly from a buffer concentration interface it in the mass spec. The other thing is the speed. I can shoot out droplets from each well in less than a second. So one can easily shoot from one well to the other in less than a second. And the third aspect, which I think is very crucial, is there is no carryover because there is no sample needle. You don't need to clean anything because you directly shoot into the stream because there is always a constant flow of solvent. This capillary is constantly being washed. So having this set up, I think this is a great system to put into in the research lab for pharmaceutical research. Let's just take one step back and give credit to the people who were involved in this project. At the beginning, we have Gary van Berkel from Oak Ridge, together with Wilmos Curtis. In 2015, they came up with this open port probe. At that time, there's a couple of publications in that. And only in 2019, SciEx was involved in that and had the first prototype, which allowed us to do some sampling directly. At that time, it was a triple quadrupole system. Obviously, it isn't that simple because there's many technical issues to be solved. And only in 2020, there was the first system introduced. It was a triple quadrupole system with the ECO system. At that time, we were interested in it. We looked into it for small molecule screening, but in my view, the combination of a quadrupole with an ecosystem wasn't really the ideal system. So we hold back and said, why don't you just couple a QTOF system to that? Because a QTOF system is extremely fast. You can use full mass scan. It's a parent mass scan, and this allows us then to do many ions at the same time, and this takes advantage of the speed of this system. And as often, SciEx listened to the customers, and last year they started working on this system, bringing that out, and this year it became commercial. So now we have this system, which comprises of a ECO, it's called the ECO MS Plus system, which is coupled in a high-sensitive ZenoTOF system, the 7600 system. In my view, a very beautiful application. If we have something new, let's put that into perspective. And I'm not coming from the screening world, so please excuse if I make some statements which are not really accurate, but I think I just want to put things into relative perspective. So in the screening world, the simplest way which you can do a screen is you do a FRET assay or some fluorescent assay, which is depends on labels. You label something, when the reaction occurs, the label changes, and then you measure optically how this reaction performed. Obviously, this is super fast because you can use imaging technologies to acquire full plates in a fraction of a second. You have acquired your data. Drawbacks, obviously, is you need the label. The label might be expensive. Some people say it's robust. It might be robust, but depending on the assay, there is also some interferences. If you go to the other side of the time scale, there is LC-MS, and LC-MS screening has been applied since many years. As we all know, LC-MS is kind of the golden standard in terms of accuracy because you have the chromatography system, which allows you to separate your analytes out, you get rid of the buffer, and you have a very good quantification. The problem, obviously, is you have a very low speed. Every sample takes at least 1 or 2 minutes to go, and that hampers the way you can do your analysis. Next step up is the SPE systems. Probably you know the rapid fire systems. So basically, instead of LC chromatography, you have a cartridge. This helps in cleanup of the sample very fast, and then you have a fast injection into a TOF. A great technology, but again, this depends on the speed which you can go. And so a typical speeds which you achieve is about 10 seconds per sample. Now, if you go to the very right side, there we have the acoustic. And so basically it combines a little bit of everything in one system. Obviously, the major advantage is extremely fast, right? Because you can shoot droplets with you can even 1/3 of a second, you can shoot droplets into your system. So you can measure your plate very fast. Again, it's label free. So there is no label. So you can measure a 384 or 1536 plate at a very high speed. There is low sample consumption because you just inject a couple of nanoliters, and that makes it very interesting. So if you put all that together, this looks very interesting. That's why we also showed interest in the system, and we spent some considerable amount of time into looking what it can bring to our lab. But before I go to my major application, the thing which we did first is basically we wanted to compare how this new system, the combination of the Echo Plus system with the ZenoTOF, compares to the combination of the Echo system with a triple quadrupole system. Because people always say, well, I want optimal sensitivity. You don't have that with the QTOF. And if you look at the published data, for example, the previous data was shown like they could measure 2 nanomolar concentration, lower limit of quantification for loperamide. In our system with the TOF, if we go just for MS, we can also get 2 nanomolar concentration. If you go with MRM mode, then we can go even lower than the triple quad. And the same holds true for the other 3 compounds which were shown, and then one of our compounds. I realized this is not an extensive panel, but that gave us an idea that basically this system has really the potential to be as sensitive, if not more sensitive, than the combination with the triple quad system. This is just briefly. The one aspect I want to highlight here is basically assay development. That's always coming. If you do LC-MS, people say there is a lot of assay development time. If you go for a rapid fire system, there is assay development time. In this system, there is basically not much which you can develop. The only thing which you can kind of modulate is the carrier fluid. So that's the fluid which transports from one side to the other side. And we have an extensive list of carrier solvents which work with different molecular classes. So within half a day, I basically can do my method development, and then it's done. So let's go to the major assay, and I think I want to spend some time on that. So that's just one example which we did. It's a covalent binding assay. The assay principle is very simple. You take a protein, you expose this protein to different small molecules, potential drug candidates, and you want to find out which ones are binding to this protein. Obviously, that's something which is difficult to pick up with fluorescence, but with mass spectrometry, it's easy to do. You measure the mass shift, and based on the mass shift, you can determine if you have 1 or 2 or multiple drugs being added, right? So here is my buffer concentration, and what you can see is basically we just took the buffer which people also take for LC-MS. So we take 150 millimolar sodium chloride or 0.5 millimolar of TSEP, something which you typically wouldn't directly inject in the mass spec. Because you have this dilution factor, you really end up with a very low concentration. At the end, you get beautiful data. So just some MS data at the back end. So in this case, you look at the parent ion scan from 700 to 200 m/z, and then we use acquisition bins of 200 milliseconds. So that results in about a sampling time of 1 second. If we can produce this data as fast, we also needed to develop some method to do the data evaluation, because if previously people did LC-MS, you have time, you can look into your data manually. In this particular case, if you go for thousands of samples, then you also need to adapt this process. And so we did our data pipeline. It's kind of conceptually simple. You just feed it with the parent mass of the protein, you feed in the molecular list of the molecules of each well, and then you look for binders. Binders are just expressed as a mass shift, so you have 1 or 2 or multiple binders. And you detect them, you detect also the sodium or potassium adducts, you add them up, and then you can now come up with your hit list. If you take, for example, a 1536 well plate or a 384 well plate, that's how it can then look. So this is the plate after hit calling. It's a very simple way to display the data. In this case, we had a negative and positive controls. Obviously, the assay can easily pick them up. You see the negative controls, there is no signal here, and the positive controls spread over the plate with the blue frame are also picked up. Now, this is a central slide, and that basically explains a little bit the assay which we do. So in this particular case, we decided to go with 384 well plates. So you shoot from each well, you shoot 4 nanoliter drops, and this takes 2 seconds from peak to peak. Then the data processing pipeline is fully automatic. So there is a peak integration because there is no chromatography. We integrate the full peak. The one thing which we do is we do background subtraction because we know how the signal of the buffer looks, so we can just directly subtract that, and then we do a deconvolution into the parent ion space. So we have the protein here, and then the adduct here, and then we do direct hit calling based on the molecule of interest, and then can process the data in the system, the screening system of your choice. So this whole process is very fast, as you can see. Now, each well here, we typically put about 25 microliter of our reaction mix. And so we shoot out for one measurement only 10 nanoliters. So the rest of the reaction is still there. And so what we can do from the same plate, we can do multiple measurement because the whole process of measurement takes only 15 minutes. We can, from the same plate, do a time series. And that's exactly what we did. So in this example, we had a plate spiked with 40 plus compounds. Each half row here is a series of concentrations, and then basically this on the x-axis we have the different compounds, and you can see after 1 hour we already have some positive hits, so which are high concentrations show some binding. Obviously then you can go on and measure the plate again and again and again. So this was measured 6 times, so over a time period of 22 hours. And you can see, as you expect, that actually the compounds start adding up to the protein. And if you look at one particular series, for example, you see at the beginning, there's only at the highest concentration, you have a significant binding, which then increases till at 22 hours. We also have at the lower concentration binding. So we have the full data set in one single experiment. So we don't even have a binding, but we also have the idea if it's binding directly fast or if it's a slow binding compound. If we look at this data in a different representation, so here is again a couple of these compounds, and you can then directly look at the concentrations. So you see they all go up over time. This is the series which we saw previous, and then you can build your kinetic curves. Just because it's a mass spectrometry seminar, we also added some mass specs. So these are the data for this particular well, how it looks at the beginning, and then when we process with our sample, how it then goes on, and how the addition of the adduct build up. So the whole experiment, in less than 1 day, we did one single plate for an experiment, but obviously you can stagger them and you could run your full assay on the same plate. We did it in this case 384, but you also can work with 1536 well plates. Because we have time, I wanted to throw in some additional data. That's lead optimization. That's basically a small molecule. So it's ADPR, and a byproduct of this reaction is the cyclic ADPR. We compared the ECO-MS system versus the very well established rapid fire system, because that's what the industry standard seems to be. At least at Novartis, we did a lot of work in the rapid fire system. We did the plate first in the ecosystem because it only takes like 10 nanometers. Then we took the plate over to the rapid fire and measured the same plate on the rapid fire system. And as expected, you can see there is extremely well correlation between the two systems. That also expresses itself if you look at the IC50 values, right? So basically we compared the IC50 values, which were deducted from the plates, and they were matched very well. Also, if you're from the screening world, you know about C prime values, and obviously the C prime values and ecosystems are all also very good. The difference really is that we need much less sample, right? So in this case, I only need like 10 nanoliters. Obviously, I need to put some in my well. If it's a 384 well plate, the minimum amount which I need to put in is 20 microliter. If it's a 1536 well plate, I can work with 6 microliter of reaction mix. The throughput is at least 8 times faster than a rapid fire system. So that makes it already a beautiful system for us to replace this. The other thing is consumables. If I look at the consumable, I need about 1 milliliter of solvent per well, which is nowadays an extreme value. In this system, this is much, much less, right? Because I just have like this 6 microliter, and then I have a little bit of carrier flow solvent, which carries it over. And so this is also a great advantage. So with this short presentation, I can come to the end. I want to leave some questions open because we covered many aspects during our experiments, and that showed just a few. And to give it a little bit of a differentiated feedback. So what we really liked is it just worked, right? The system was installed. Many of the assays which we previously did with the LC-MS directly were transferable to the system. One, for example, these lead optimization assays, they work. If they work for rapid fire, they work beautifully on the ecosystem. It's extremely easy to use, right? Because there's not much which you can change. It's the carrier fluid which you can change, but everything else is just the mass spec parameters. That's something which are given by the molecule which you want to analyze, and then it's there. The other thing is basically the walk-up time. You just walk up, switch it on, let it equilibrate, and then you can go, and then you can go for hours with this. As I said, I want to be a little bit differentiated, and so we had some issues with buffers in the 1536 well plate. Basically, some buffers they had, or some proteins were sticking to the wall of the plate in 1536, and so basically the surface wasn't really even, and then the drop would not hit the interface. We spent some time in figuring that out, but at the end, the solution was very simple. We let the plate settle for some time. The surface would then even out, and then if you let the plate sit for an hour, then you can shoot from the plate, and then you get all the droplets into the system. Now, one issue which you might think is not really an issue, so the instant capacity is really too high. And why would that be an issue? Well, in our world and pharmaceutical industry, we always look at cost and how you want to optimize processes. And then how are you going to feed a system like that? Because you don't have so many chemists. Let's say you want to do lead optimizations. You just cannot feed the system. If you can measure, let's say, 1 million compounds a day, who's going to produce 1 million compounds a day? So the system is actually very good suited to be used for multiple applications because there's no cross-contamination. You can easily switch between one and the other. Then the end, and that's something which we really don't want to see. Yes, lower sample volumes. So the measurement takes about 10 nanoliter of protein solution, right? And we still have about 6 microliter left at the end of the measurement, because that's the minimum volume, right? And so that's a call to the guys at Danaher, which produce the ecosystem. So if there is a way to minimize this volume, then we could get away with a lower concentration or a lower amount of protein in each well, which would make it even more attractive. And the other thing is obviously some technical things which I just want to put out there. So I think the system is great. If some things were to change, is the carrier solvent selector is like having a quaternary pump versus a binary pump. It's nice to have, but it's not really necessary. So at the end, conclusion from our evaluation, I think there's many applications where this system has a huge benefit for biomedical research. Lead optimization is one of them. Covalent binding is another one. There is also work which we did in non-covalent interaction, which is very attractive. There is more work of this to come. And I think with that, I'm at the end of this presentation. I'd like to thank you for staying and listening to that. If you want to learn more, we currently have a manuscript which was submitted. We got it back. We do minor revisions, and I hope this will be published within a few weeks. And then there is more detail on this particular assay and the data processing pipeline. Thank you.